All righty, well, you guys have a derivative you have to work. Which, by the way, I found out over the weekend, if you're not watching the new Mall series, you need to watch that.
What is it?
Oh, yeah. See, that's one of those things. Asking me who or what mall is one of those things that you say that, I hear I don't want to graduate. Are you?
Yeah.
You can make fun of a lot of things. You cannot make fun of my Star Wars cartoons. Okay, so let's look at this. How do we do this derivative? Okay, well, the derivative is going to pull inside the brackets. Okay, so that EMF of the battery over R is a constant. You can do the full proof of the chain rule when you take calculus. Otherwise, just move the constant to the outside. Now, so what we're going to get the derivative of the 1 minus and so the derivative of constant is 0. So we need to figure out this derivative here. So we're going to use U substitution again. All right. So you have a constant times T. So that is going to give you negative R over L. Okay, and then by chaining, yeah. So that's going to give us okay, well, we have du dt. That right here. The derivative of an exponential just gives the exponential back. So du dt is negative R over L. And ddu of EU is EU. And then we're just going to put our U back in.
I know.
So that means that okay. So if we go back up and we think, well, what were we looking for? We were looking for this whole thing here. Okay, so okay, so what is that? Alrighty. Which is going to give us okay, so we saw that derivative of the current. Now remember, so what we were looking for the EMF of the inductor, and that was L d-I-dt. Going to be L, EMF of the battery over L, minus RT over L. So our EMF of our inductor and there we go. And so we've been looking at charging the inductor, but after the EMF is removed, where the hell did it go? There it is. After the EMF is removed, the current in our inductor is going to discharge the current in the inductor will discharge by that equation. That's all the harder you hit, your anger is not that scary. I don't remember why I put so much space in there, but alrighty. So look here. There's a fun unit for you, a 0.67 watt. What is that unit? Millihenries.
Oh,
Once again, you say 6, 7, I hear I don't want to graduate. I'd be willing. You want to roll those dice? You're going to hit on a natural 1 there. So we have a 0.67 millihenry inductor and a 130 ohm resistor placed in series with a 24-volt battery. So that's fun. We have a circuit. We have a circuit here. How long will it take for the current to reach 67% of its maximum value? What is the maximum energy stored in the inductor, and how long will it take for the energy stored in the inductor to reach 67% of its maximum value? Okay, so what does this look like? So, okay, I mean, maybe something like that. They're in series with each other. Okay. So part A is saying, what is T when okay. So we go back to our charging equation for current. And so we have to solve for T when I equals 0.67 IF. So this is going to be 0.67 IF. All right, so it's going to be 0.67, 1 minus E. Then we have to solve for T. And it's buried inside that exponential. And so then from here, you can plug in your numbers. So the inductor Okay, what does B ask us for? What is the maximum energy stored in the inductor? Okay, well, we are looking for one half Li squared, where I is E over R. Where did I get that I equals EMF over R? No. It's Ohm's law. Alrighty. So what, 0. So the energy stored in the inductor is 1.1 to the negative fifth joules. And part C. How long will it take for the energy stored in the inductor to reach 67% of its maximum value? Okay. So now we have to kind of combine two things here. All right. Now let's see. 1/2 L. Now look at that. Look at that there. 1/2 L I final squared. What is that? What does that look like? Yeah, it's going to be that final potential energy, whatever we charge to. And we're saying, what is T? So just like the first one, we just needed a new equation. The first thing I'm going to do is square root both sides. Going to give me 1 minus E. Square root of 0.67. Oh, So that square root minus 1 is going to give negative 0.181. Okay, so then we're going to get rid of the negative sign. Take the natural log of both sides. And then our t is going to be L over R times 1.71. So 8.81 times 10 to the negative 6 seconds. All righty. So that finishes up that chapter. So the next chapter we're going to cover is electromagnetic radiation on orthogonal manifolds. I really kind of expected people to spaz if I said something about a third chapter of magnetism. Because I know magnetism is usually everyone's favorite topic because it's so easy to understand. I had to make last Friday's homework difficult too because the light ones should not be that hard. So do what? The one that's due this Friday. Yeah, I guess it depends on how you look at difficult. Would what? A seventh grader would find it impossible. But you guys are juniors in various medical sciences. Okay, so light. Wavefronts, rays, and oh, there's another one of those fun European names. Someone pronounce it for me. It's Huygens. Was that a satellite or a space probe that we named Huygens? Anyway, same guy. I think it was it a space telescope? I don't know. So light is, of course, electromagnetic radiation. It allows you to see, it transmits energy. Now the textbook says it's the spectrum of light that's visible, and that's just not true at all. Because there's X-rays, there's gamma rays, there's radio waves. Everything in light is transmitted by the photon. The photon is the electromagnetic force carrier or the electromagnetic boson. It behaves as both a particle and a wave. Just because you can see something does not mean it's a source of light. Despite what some people think, the moon does not emit its own light. What does emit its own light? The sun. Yeah, once you heat it up, well, where does the light come from? You heat up the filament, what happens? Well, that's an older light bulb. Now it's like these gas-filled ones. You hit them with electricity. Oh, that one's going on a quiz. We covered that in freshman chemistry. Where the light comes from. Yeah, you what? If it has a filament. Otherwise, it could be compressed gas. Yeah, but where's the glow come from? It is kind of a chemical reaction, kind of. See, the thing that makes the filament glow is the heat. So then you see that heat represented as photons because of a certain process. Yeah. You know, phosphorescence is the same kind of process. Fluorescence is the same kind of process. You guys aren't answering that. So you guys haven't taken biology classes either. I'm telling Hardy. I'm telling Hardy, I asked plant questions and they had no idea they looked at me and said, what's a plant? That's what I'm saying. That's what I heard. Okay, wavefronts. We got to start thinking of electromagnetic waves in terms of wavefronts. A wavefront is going to be a set of points of equal phase separated by a distance lambda. What is lambda? A bunch of people said a bunch of things. Who said it? Yeah, wavelength. So what do we mean points? Points all at the same phase. I mean, yeah, they're definitely going to be at the same height on the wave. So not, oh, well, that's bad. Typical sine wave. Okay, so well, let me draw several of them. So for example, points here, here, and here are all at the same phase. So that would translate to here. On a sine wave, what angle is that? 90 degrees. This here is 270 degrees, 180 where it crosses the zero line. You could have another set of points here. You could have a set of points at 180 degrees. So if you have two waves shifted in each other to where their peaks and troughs don't line up, those are out of phase with each other. They're at the same phase if they all line up at the same angles. Yeah. So it's just points, it's several waves that are lining up and their points are going to be like that and they create these wave fronts. Well, you're not there, but they're separated by lambda. The next one would be there. So then when we're working with light, we're going to be working with we're going to be using diagrams called ray diagrams. And that's kind of what you see down here at the bottom right. We're going to represent light with rays. Now is the time during the semester, if anyone wants to bring in laser pointers and screw with your classmates, it applies to class. I'm not going to say anything. Well, bring the laser pointer, see which one of your classmates you can get jump at it. Yeah, don't put lasers in the eye. Okay, so Huygens principle. We're going to be thinking of wave fronts as a combination of a bunch of little wavelets. And so every point on a wavefront is going to be the center of another spherical wave. And you'll have that center at time t, at some time t plus delta t. The wavelets have traveled a radius of v delta t, or in this case, v is what? Remember your kinematics, delta x is going to be v delta t, but what are we changing v into? Yeah, what is that? Yeah, what is c? You guys have been saying this equation all year, and now all of a sudden, huh? Nope, that's big C. This is little c. There, yeah, what is c? Nope. If I replace v with c, what is c? You should know. You guys are going to smack yourselves when you hear it. Yeah. If v is c, what do we call c? So what's moving? It's a wave of what? Speed of light. Uh-huh. Noted. I will speak slower from now. Okay, so each little wavelet is going to travel a distance ct. Now you can do this for plane waves, or you can do it for spherical waves, which you see on the right. And so your next wavefront is going to be a tangent line connecting all of those little wavelets. You can kind of think of it as, imagine you take like a line of rocks, you drop them all in water at the same time. And you see how their waves like start, those rocks are going to be your points, and the waves propagating out, you could connect them with a straight line. All right, the reflection of light. We have two main types of reflection, specular reflection and diffuse reflection. Specular is going to be on a smooth surface. It's going to hit and it's going to reflect. The angle of incidence is going to equal the angle of reflection. Incident means the light ray that is coming in and hitting the surface. Diffuse reflection is on a rough surface. This is most of the reflection that we see. And so the incident light hits it and it scatters in all different directions. The laws of reflection. Angle of incidence equals angle of reflection, and they're always measured from the normal to the surface. What is the normal to a surface? What is the normal? Yeah, it's a line perpendicular to the surface. So you see here your theta I equals theta R, and they're measured from that normal. Then, of course, they all lie in the same plane and so on and so forth. All right. So let's see here. We have two mirrors. They're going to make an angle of 120 degrees with each other. Okay, so I'm going to draw that mirror. And I'm going to draw that mirror. Okay. And one and two. Okay, a ray is incident on mirror one at an angle of 65 degrees to the normal. Find the angle the ray makes with the normal of M2 after it's reflected from both mirrors. Okay, so we say it's going to come in and hit the mirror. Then it's going to come out. Then it's going to hit that mirror. And then it's going to go that way. So it's coming in that way, reflects, and then leaves. And someone did this last year. Don't do this because I'll mark everything wrong and then I'll make fun of you. Someone decided to they couldn't solve the geometry in a homework problem. So they said, well, I just assumed that I drew my straight lines and the ray ended up missing mirror two. So there's no angle of reflection. I was like, yeah, no. Now the normal to the surface are going to be these straight lines perpendicular to each mirror. Or as perpendicular as I can make them. Okay, so we have theta I, that's our incident angle. That's 65 degrees. We know by the rules of reflection, theta R, what does theta R equal? 65 degrees. I also know The mirrors connect at a 120-degree angle. What I don't know is that angle, that angle, our second incident angle, and our second reflection angle. We're looking for, the question wants us to find, what is that second angle of reflection? So, a bunch of geometry. Why is that Maggie's fault? like, you don't know geometry and it's Maggie's fault. Well, what was that? What was that TikTok? The round peg goes, that's right, in the square hole. In the square hole. And this little half circle piece goes, that's right, in the square hole. Uh-huh. Yep. Okay, so I'm not going to ask because I really don't want, I just don't want to know if you don't know. So I'm going to tell you, in the center, that's a triangle. It's a parallelogram missing a side. Okay. Okay, so to even begin to figure out our betas, we have to know phi and alpha. Is it? No. Oh, there you go. See that, so normal one. Well, let's not call those ends. We're going to use that for something else. Well, 1, 2, normal one. So that normal line there, you see that theta r plus phi is 90 degrees. So phi is going to have to be 90 minus theta r. 90 minus 65. Phi is going to equal 25 degrees. Okay. How do I find alpha? Yeah, every angle of a triangle has to equal 180. So phi plus alpha plus 120 equals 180. So alpha is going to be 180 minus 120 minus phi. And when you plug in phi, alpha is going to come out to be 35 degrees. Now, how do I find the new angle of incidence? Yep. Alpha plus beta incident, 90 degrees. And so that's 90 minus 35. 55 degrees. Now, how do I find the angle of reflection, the beta r? Is what? Yep, due to the laws of reflection, beta I equals beta r. And so then the answer to this problem is 55 degrees. We're going to squeeze in like another 5 minutes. No, we're not. So this is what you need to get used to for these sections. This is geometry.